In this video, we will learn how to draw a dinucleotide. As a quick reminder, a nucleotide is a building block of nucleic acids. It's the monomer of nucleic acids. Some people call the nucleotides bases, but bases are actually one of the three components that makes a nucleotide: a base, a ribose sugar, and the phosphates. And what you're going to need for this project, you will need a blank page, okay? We will be making 3 drawings of 2 dinucleotides each. And each set of nucleotides will probably take about half a page of your notebook to complete. So I recommend using colored pencils or pens to do the drawings so that we can keep track of the electrons as they move from one atom to the other. And I will be showing you now in the next few seconds. I will be showing you what your first set of drawings should look like. I'm going to use a green color to point one nucleotide. So this is a mononucleotide triphosphate circled in red. This is a second mononucleotide triphosphate circled in blue, okay? So your next image, your next drawing should look something like this. We will be explaining, I'm going to be using the purple marker. We will be explaining the ester bond formation, the new ester bond formation. As you can see, I'm using this big purple arrow right here. And the green represents the ester bond formation between one nucleotide with the other. This is a condensation reaction, so a water molecule will be leaving. I'm going to be circling it in orange right here. And also a pyrophosphate will be leaving. Okay, so we will be explaining the intermediate steps and you should be able to draw the ester bond. And your last image should look something like this. Your last image should be showing exactly what happens at the end of this whole process. At the end of the whole process, I have here used the green arrow right here, upper nucleotide, okay, bottom green arrow, lower, okay, nucleotide. Let me circle them. So this is the lower nucleotide, the upper nucleotide, okay. In purple, you can see the phosphodiester bond forming between the 2 nucleotides. In red, you can see each single ester bond that already previously, this one, let me use the red marker, already existed, and this one is the newly formed one. So all together, I'm going to circle it in red, it makes the phosphodiester bond. So now that you've seen all of that, let's get started from scratch. So let's get started by drawing a sugar ribose. So we're going to put an oxygen. It's similar to a cartoon house with a chimney on it. We're going to put carbon 1 prime, carbon 2 prime, 3 prime, 4 prime, and the chimney, it's 5 prime. Attached to the carbon 1 prime, you have a nitrogenous base right here. I'll just write base on it. And carbons have 4 bonds, so if we count 1, 2, 3 bonds around carbon 1, so here is the 4th one with the hydrogen, okay? And let's add the functional groups to the carbon. So this carbon 2 already has 2 bonds, and we're going to add 2 more hydrogens. As you can see, I'm drawing DNA, deoxynucleotides, so I'm not going to put an oxygen if I were drawing an RNA nucleotide, there would be an oxygen there. And on the third carbon, it has a hydroxyl group and a hydrogen. And the fourth carbon has just a hydrogen. The fifth has two hydrogens. And there is an ester bond right here. And you can see it is attached to an alpha phosphorus atom. Okay, so right here, and this one is united to a next one and to a next one, and we have an OH here. We're going to put double bonds on the phosphorus atoms, and I'll put OH for simplicity reasons at pH 7. There is between 1.4 and 2 negative charges, so I could put O negative, but for simplicity reasons, I've used OHs right here, okay? So a phosphorus group is, you can see a phosphorus atom, and it's attached to a bunch of oxygens, okay, right here. So this is a phosphate group, what I have circled in red and dotted in red. And these are two more phosphate groups right here, okay? And the next thing that I would like to do, I'm gonna draw the next nucleotide in red so that you can differentiate the two. Here is a phosphorus atom, and these bonds can flip, so it doesn't really matter which order I put them in. And if you remember, it is connected to the fifth carbon, so pay attention, please, as you draw it. So here we have carbon 5 prime, okay, and it's connected to carbon 4 prime. 5 prime is supposedly the chimney of the house. 1 prime, 2 prime, 3 prime, 4 prime, and I'm going to add all the hydrogens. This one has a hydroxyl group and a hydrogen. This one has a hydrogen, and this one has a hydrogen and a nitrogenous base right here. And this phosphorus atom, okay, we have more phosphate groups right here. So I can flip these bonds around. So I'm going to keep these the way the upper ones are, okay? And so at this point, what I would like, so your first set of drawings should look something like that, okay? And you can see I'm going to circle the nucleotides in blue, one nucleotide, and in green, the other nucleotide, right here. And please pay attention, I'm going to use the purple marker, pay attention to this area right here, because this is where the ester bond will be forming, okay? So at this point, I'm going to erase it, okay? And I'm going to draw from scratch all over again the upper nucleotide with the oxygen, carbon 1 prime, 2 prime. If you're wondering why are they primes, it's because, as you can see, attached to the carbon 1, there is a base, nitrogenous base, that also has carbons. And these carbons are not marked as primes. So the primes of the ribose, we use the prime to differentiate them from the bases. So here is C2, C3, C4, and here is the chimney, C5. And here already we have an ester bond right here, okay? But now the process of uniting one nucleotide with the other nucleotide involves the formation of a new ester bond. So we will be paying attention to the formation of the new ester bond. Okay, so I'm lining up now the alpha phosphorus. I call it alpha, that's the one that is closest to the 5 carbon. So here is 5 carbon, the chimney of the ribose. Here is carbon 4, and we're going to move down to carbon 3, they're all primes, carbon 2 prime, carbon 1 prime, and here we have the nitrogenous base and another hydrogen, 2 more hydrogens here, a hydroxyl group here with a hydrogen, and because it has carbon has 4 bonds, there's 1 more here, and carbon 5 has 2 more right here. And now the phosphorus has the OH here. We're flipping this around, and then here are more phosphate groups, and right here I'm going to be using a blue marker, okay, to show you this oxygen right here, okay, a pair of electrons, there is a neutrophilic attack. I'm going to write it here, neutrophilic attack. A pair of electrons, okay, will attack the alpha phosphorus atom. Why is this important? Because this leads to the ester bond formation. At the same time, a pair of electrons will be leaving this double bond and attack this oxygen. So I'm going to be using a red color to show you, because this particular oxygen of the hydroxyl group loses a pair of electrons, it becomes positively charged. This one gains a pair of electrons, it becomes negatively charged. What's important to us now, let's pay attention one more time. I'm circling in green. This is the upper mononucleotide, and this one below, it's the lower mononucleotide, okay? But in purple, I want you to see there will be an ester bond forming between this oxygen of the hydroxyl group and the alpha phosphorus atom below, okay? This double bond is lost, but then it gets reformed. It gets lost when the pair of electrons migrate to the oxygen. As this double bond gets reformed, what happens? The pyrophosphate, okay, or diphosphate, I'm going to circle it, we call it PPI, leaves, okay? Also, a water molecule, also in purple, I'm circling it, leaves, okay? So this is a dehydration synthesis or condensation reaction where a water molecule leaves, a pyrophosphate leaves, and an ester bond, ester, okay, and more precisely, phospho ester bond is formed, okay? A phosphoester bond is formed. So this is what your second set of nucleotides should be looking like. So the final product, I'm gonna start from scratch again. The final product should look something like this. So you have our ribose sugar, carbon 1 prime, 2. I'm going to draw kind of fast, but By now, you should be experts at this. Okay, this one is connected to the nitrogenous base, if you remember. And because it has to have 4 bonds, you always have to count them when you draw. This one has the hydroxyl, but because the hydrogen left with the hydroxyl group, now this one is connected to the phosphorus atom, to the alpha phosphorus atom of the next nucleotide. Okay, this one still has the triphosphate. Double bond, double bond, double bond. And I'm putting OHs here. Okay. And this one is already had an ester bond, an old ester bond, with the 5' carbon. Okay, so here we have 4' carbon, 3' carbon, 2' carbon, and 1' carbon. And this one is connected to the nitrogenous base and has another hydrogen, 2 more hydrogens here, a hydroxyl group and a hydrogen. And this one has 1 hydrogen, this one has 2 hydrogens. Okay, so the important thing here, okay, is this one has 1, 2, 3, okay, it has 5 bonds, and I'm gonna make them in blue. 1, 2, 5 simple bonds, 3, 4, and 5. This is a double bond. I don't know if it's clear to you or not, but it is a double bond. There you go. And at this point, I also want to show you the PPI, the pyrophosphate, has left. Okay, the water molecule had left. And we have a dinucleotide that has formed, okay? So, because there are 2 phosphoester bonds, okay? So I'm gonna use the red color. So you can see 1 phosphoester bond here. Let's call it the old phosphoester bond. And this one, okay, is the new phosphoester bond. And because there are 2 of them, the whole thing, I'm going to make it green. We call it the phosphodiester bond uniting the 2 nucleotides. I would like at this point for you all to be able to look in your book, okay? In your book, there is an image that shows you the condensation reaction, and you can see how a water molecule leaves for 3 phosphates to be united to the 5' carbon of the ribose sugar. And this is the nitrogenous base, okay? Depending if you're talking about DNA or RNA, in this case, I can see that we're talking about DNA because the second carbon doesn't have a hydroxyl group. So in the case of DNA, the nitrogenous bases are adenine, thymine, cytosine, and guanine. But if we were talking about RNA, okay, then instead of thymine, you would have uracil, okay? And this is a mononucleotide triphosphate. This is what you started your drawing with. If you remember, your first set of drawing had 2 of these together. Let's move to the next image in your book. The next image in your book should look something like this, okay? And you can see this one has a an oxygen, a hydroxyl group on the second carbon, so I know this must be an RNA nucleotide, okay? It's not a deoxyribonucleotide, but it's a ribonucleotide. And you can see also that the nitrogenous base on carbon 1, it's uracil, okay, instead of thymine. And you can see the 3 phosphates right here on the 5' carbon. And finally, the last thing that I wanted to show you, the formation, okay, of a strand of nucleotides. So pay attention. Sometimes students are confused about 5' end and 3' end. The 5' triphosphates, okay, they contribute, right here, they contribute the energy to form the ester bond, okay? And this explains why only nucleotide triphosphates are added to growing nucleic acid chains. One cannot break a phosphodiester bond and then reform it, because the triphosphate energy can only be spent once, okay? So cells do their best to get it right when they add new nucleotides to the nucleic acids, because it is expensive to make a mistake. So you can see this is the 5' carbon, and it has a phosphate attached to it. That's why we call it the 5' end. On the other hand, do you see right here the hydroxyl group? This is carbon 3. Do you remember our drawing? So this is the 3' end of the chain of nucleotides, okay? And the chain is always growing 5' towards 3'. Because as this bond breaks right here and the pyrophosphates leaves, that gives enough energy for the nucleotide to be added to the growing chain.